Chemical bonds are formed when a system of atoms is more stable together than it would be apart. In most types of chemical bond, balancing electrostatic charges is responsible for most of the increased stability. Ionic bonds are one extreme case, where each atom claims its full set of electrons for itself and opposite atomic charges attract one another. The balancing of atomic charges then leads to the formation of neutral salts. At the other extreme are covalent bonds, where one or more electrons are shared in the valence shells of two or more atoms. Because this increases the electron density between the positively charged nuclei, the atoms stay closer together than they would if they were not bonded. In fact, the distance between the nuclei is a good indication of the strength of the bond. But which atoms will share how much with which other atoms is a bit more nuanced. The process of building Lewis dot diagrams boils down some reliable rules of thumb into a pretty easy to use algorithm. Follow the steps and you'll end up with a good approximation of the real molecular structure. We'll use water for our first example. For step 1, we want to count up all of the electrons in each of the atom's valence shells and then sum them together. That's going to be our electron budget for the entire molecule. So in water, we have 2 hydrogen atoms, so that's 2 electrons, plus 1 oxygen that gives 6 electrons in its valence shell. That's 8 electrons in total. In step 2, we're going to draw a skeleton of what we think the molecule might be. So first, we're going to draw the central atom. That's the one that has the lowest electronegativity that isn't a hydrogen atom. Hydrogen atoms are always terminal. So in this case, we only have oxygen and hydrogen atoms. So oxygen has to be the main central atom, and the hydrogens have to be the terminal atoms, or the ones that are going to attach to it. So since nature loves symmetry, let's draw hydrogen atoms bonded onto that oxygen atom across a line of symmetry down the middle. In step 3, we have to subtract each of the electrons that we've used to make those bonds from our electron budget. So each one of these bonds takes 2 electrons. So 2 bonds times 2 electrons is 4 electrons in total, leaving us with 4 electrons remaining to be placed. In step 4, we place the remaining electrons around the structure as lone pairs, starting with the terminal atoms. Hydrogen can only take 2 electrons in its 1s orbital, so its single bond to oxygen provides it with the 2 electrons it needs to complete its shell. That's why hydrogen is always a terminal atom. Since we have nothing to do on this step, let's just go straight to step 5. In step 5, we put all the remaining electrons as lone pairs around the central atom. So this gives us 4 electrons to place around the oxygen as 1, 2, 3, 4, 2 sets of lone pairs. And so with that, we've exhausted our electron budget, and this should be a complete structure. In the final step, we want to make sure that the structure that we've drawn satisfies the electronic needs of all of the atoms that make up the molecule. So hydrogen has 1 bond each. That's 2 electrons for hydrogen, filling its single 1s orbital. So each of these hydrogens are going to be okay, just by virtue of that 1 bond. That's why they're always terminal atoms. The 2 electrons in each of these bonds also count for oxygen. So that's 2 times 2 electrons for the bonds, and 1, 2, 3, 4, 4 electrons in the lone pairs, or 8 for oxygen altogether, satisfying the octet rule, but more importantly, satisfying the number of electrons that oxygen can hold in its valence orbitals, in its 2s2 and 2p6, or 8 altogether. If it were the case that one of the central or terminal atoms has not completed its valence shell, then we would be able to move some of those lone pairs into multiple bonds. We'll run quickly through 4 more examples. Like last time, pause the video at the introduction of each one, try it yourself, then use the video to check your work.